Okay, welcome to the next set of slides. This is probably going to be a very chill week. These two data structures that we're going to talk about, these two ADTs we're going to talk about really, are not too difficult. They're pretty simple given what we know because they're just more list stuff really. These are the last ones. So before we get into queues and decks, those are fun words, queues and decks. Let's talk about stacks just one more time before we get into the main part of this lecture. I want to make this thing called an RPN calculator, and it is a good use case for stacks. Boop, boop. So RPN stands for Reverse Polish Notation. I don't know if the Polish invented this, some Polish person, who knows. All I know is that's what it's called. And let me give you some background. So there used to be fancy calculators. Like back in the day, everybody was using like slide rules and things like that. Abacuses, abaci, whatever. And then we had the invention of the calculator. So mighty, so tiny. And it was super expensive back in the day. This is an HP calculator. And HP used to make these awesome little calculators that everybody wanted back in the 70s. So the way that it worked, though, was not like a normal calculator that you know about, where you press 2. You can't see that at all, can you? Let's keep this white for a little bit then. Or you press the 2, then you press plus, then you press 2, and then there's like an equal sign somewhere, or an enter. No, that's not the order. That's not how that worked. Instead of that, you had to do 2 enter, 2 plus. So you type the 2. It's the weirdest thing. Type the 2, then the enter, then another 2, then the plus to like finish it off, and it would show the answer of 4 on the screen. So that's an interesting concept. You may have never heard of that before. It's called reverse Polish notation, and it uses a stack actually, and the operator, that plus at the very end, it was like, pop the stack. Okay? Let's see here. So let me, I guess, give you an example of how this was working back in the day. So this calculator used a stack, and that was, I guess, easier to implement on the little chips, or probably the large relative chips that they used back in the day. So let's do 5 plus 7 times 3 divided by 8. And remember the order of operations. We gotta do these ones first, right? So, boop. Let's make this happen. Well, alright, if I want... Actually, let's do 2 times 2 first. Let's do it back here. Let me show you how this works. So, you have a stack of operands. It's called an operand stack. And the operators do not get pushed onto an operand stack. So it's empty, then you type your 2, hit enter, and it pushes it. And then you type another 2, which is implicitly pushed when you press the plus. And then when you say plus, when it sees the plus, your program, the second it sees this, because it's looking at like, I don't know, a stream of characters, like 2 enter, 2 plus. And then once it sees the plus, it's like, I need to do this plus operation. Let me pop the 2 things off my stack. Let me pop the top 2 things off my stack and then add them. Okay? So pop 2 things off stack and add them. Let's see here. Let me make it green now. So the second you press that plus, it's going to be like pop, pop. And the first thing was the left. So it's like 2 plus 2. And then suddenly you have the answer of 4. Okay? And it prints out 4. Well, that's almost what we're going to do. Because once you have more than 2 operations, you're going to want to push the result back onto the stack. Okay, let me show you that. So we're going to do 5 plus 7 times 3 divided by 8. Alright, so the first thing that we're going to do, well, let's convert this first. How do you convert this to the old HP calculator reverse Polish notation form? Well, it's going to be, these need to move too, darn. It's going to be 5, enter. I'll draw like a little enter sign like that. 5, enter. Then we do 7 times 3. So 7, enter, 3, and then we do times. Okay? And these enters are kind of implicit and useless, so I'm going to get rid of them now. So really it's 5. Anytime you see a number, you just push it. So 5, then 7, 3 times, because the times will get the latest two things, so it'll do the 7 times 3 first, and it'll push it back onto the stack so that we can then add the result. So it'll have 5 and then the result of this. And I'm going to show you this working, don't worry. It makes sense, I promise. And then I have the result of that back on the stack after I've added it. And I'm going to push 8 and divide. Okay, so that's how you convert this. And let me show you why this makes sense and why it's working. So your program, when you write it, when we write it right now, after this, we're going to look at the first character. All right, we're always going to be looking at a certain index into whatever we're doing. So we're going to look at the thing that we're trying to operate on. Either it's an operator or an operand, and it's an operand this time. So I see a 5. It's not an operand, or it's not an operator, so I'm going to push the 5 to my operand stack. Okay? So I'm going to do that. Push the 5. Done with the 5 now. Moving on. See the 7. It's just another number. It's an operand. Push it. No, see a 3. Just another number. Going to push it. And this is where the magic happens. Star pops the stack. Okay? So it sees an operator. It forces a pop. Honestly, forces 2 pops. It's going to look at the top, get it off. It's going to pull out the 3 by popping. And it's going to pull out the 7 by popping. And it's going to multiply them. And the 7 came first, so it's going to look like this. Let me put it in order. It'd be like, boop. Oh no, I didn't want that. It's going to be 7. There we go. 7 times 3. The 7 was on the left, because it was the first thing popped, or pushed. Okay, so that will make 21. So we get 21 out of that, and we're going to push it back onto this stack. So what's going to happen is we popped these things. They're gone. But we just created 21 out of both of them, so we're going to push it back. Push the result back. Okay? So now we have 21. And we can move on. Okay, so with that, let's now do the next thing. Now we have a plus. Again, it's going to pop twice. It's going to be like, pop, pop. Get the 5, get the 21, and add them together. Okay, 26. Cool. So now I have an empty stack, and I just created an answer. Oops. Of 26, and I'm going to push it back on. Okay? And then I'm done with the plus. Then I see the 8, push the 8. Alright, so I got 2 things on the stack, and then I see a division, so I'm going to pop 2 things off the stack. I'm going to pop the 8 and pop the 26, but I am popping the 8 first, of course, because it's on the top, but the 26 was supposed to be on the left because it's before. Okay? I do 26 divided by 8, and let's just do integer division. It's easier for me. 8, 16, 24. So it's going to be 3. 3 point something, but let's do integer division of 3. And then we push the 3 back on the stack. And now, when we see that we're done, we should have a stack with just one thing on it, and that's the answer. Should be the only thing left on the stack. Okay? So, hopefully that idea makes sense to you. Let's go and implement this algorithm, or talk about how it's going to be implemented. So you're going to read a bunch of numbers / operators. Okay? Every time you read a number, push it to the operand stack. Okay, that's the algorithm. Every time you read a operator, pop the stack twice, assuming it's a binary operator, perform the operation on those 2 values, and well, taking care which is on the left and the right for minus and division. And then push the results back on the operand stack. Because it's very possible that I want to use that result, like the 7 times 3, I want to use that result and add it to 5. Okay, so I got to do 7 3 times, then it'll get pushed back, then I want to add. Okay, so I hope you see the ordering now, it makes sense. Alright, so that's the idea. And then at the very end, once you're done reading things, you should have one thing left on the stack. And that's the answer. Now you get back, or display on your fancy old school calculator screen. Okay? So let's go and code this up using just normal C++ stacks. And that'll be that. Let's go over here, make a new folder. 13 Vim. What do we want to call this? I don't know, calculator. .cpp. So I'm going to include stack. And that'll be that. So I guess, how do we want to get our information? Do we want to get it from the user, perhaps? Because that'll make things a bit odd. I know. How about we just pretend that the user can only ever type single-digit things? That will solve this problem. You can get fancier, though. Obviously, I encourage you to fix this. So, what I'm going to have is my operand stack, so make operand stack. So it's a stack of ints, call it S, and now I'm just going to keep reading input. So let's see here. How do I want to do this? While actually, we can make it work for multi-digit numbers. We'll just have to ask the user 2 things. I don't know. So while true, let's see here. We want to loop and do a few things. Let's ask the user if they want to quit, type a number, or type an operator. We're going to have to section it off like that. That'll solve my problem. And then do the rest of the work, depending on what they gave us. So cout type q to quit, n to enter a number, or o to enter an operator. Okay. So choice, char choice, seeing that. And so now we have their choice. If it's Q, then we're done. Let's break out of this loop. Then we'll end up down here, and we can print out the answer. All right. Otherwise, goody is n. Let's ask them for that number. And we'll use ints, get that number. Then we're going to have to do stack stuff with it. Push it to the stack now. And then, so that's as simple as s.push n. Okay, else, let's just assume choice was O, and they didn't like have a typo. So now they're typing operand. So if, no, I guess we'll have to get that operand now. Operator. So now I have the operator. So if OP is equal to plus, do something, else if OP is equal to minus, do something, else if OP was equal to, oops, star, and then just else. We can assume that they didn't make any typos and they meant divide if they didn't type any of those, and it was divide. Okay, that should do it. One thing that we can pull out of these if statements is we're always going to pop the stack twice. Let's do that now. So let's get those get those two operands to use this operator on. I will forever confuse those words. So int second oper equals s.top, s.top, and then first operand, and then s.pop one more time. Okay, so remember the reason I'm doing this. Because the left-hand side of this operation is going to be pushed first. So it's going to be underneath the second thing. So if I want to say 2 minus 3, I'm going to say 2, 3 minus. And so first I'm going to have the 2, then I'm going to have the 3. This thing that I get off the stack first is the right-hand side. So it's the second operand. Okay? So get it, pop it off, and then get the first one, pop it off. All right, so now I've got them. I pop the stack. So now depending on the operation, I'll create my result. So int result. So if it was a plus, the result is first operand plus second operand. Okay? And obviously addition is commutative, so it doesn't really matter here, but it will matter for these other ones, like minus and division. Okay. Alright, so your minus, your division, and, no, sorry, your multiplication, your division. There we go. Okay, so now I have the result, and we gotta push it back on. Just in case we need to use it later, or we want to retrieve it. So let's get it and push it back on. So s.push result. Okay, so let's see here. Save that. Where does that end? That's the else case, the operation case. All right, that's the end of our loop. We will quit once the user is done with us. And then we should have a result on our stack. So if s.size is equal to 1, the one thing on the stack was the answer. Okay, so it's ever on the top. It's that one thing. Otherwise, somebody messed up. And one thing left on the stack. Something is wrong. Either you didn't put enough information, or like you didn't type in the stuff correctly. Okay, so with that, that looks like a program to me. Let's see here. We'll find out if I did anything horribly wrong, but let's try it out. Let's go back up to the top so I see what's about to happen. So, oops. Oh, I had this. Let's see if I can. 1, Oh no, did I do the wrong thing again? Did I not CD into the proper folder? Sure didn't. Alright, move calculator into lecture 13. Go into lecture 13. As we were. Alright, / calculator. Alright, let's do this. Let's do this one. 5 plus 7 times 3 divided by 8. So 5, 7, 3 times. No, sorry. I got ahead of myself. Number 5, number 7, number 3, operator times then plus 8 divide. So operation plus, and then it was 8, right? So number 8, operator divide, quit. The result was 3, yay! And it works. I encourage you to change this code, like print out the stack as it changes. Let's see, how do we want to do this? Let's do 2 minus 3. Why not? So that's a number 2, a number 3, and then operator minus quit. It'll do the operation, and we get -1 left on our stack. And if you do something silly, like push some numbers or have some work left on your stack, like number 1, number 17, quit. It's like, more than one thing is left on the stack. You done messed up. Okay? And so every time we read a number, we push it. Every time we read an operator, we perform the operation after popping the stack and pushing the result. Okay? And once we're done, we got one thing left on that stack, and it is the answer. Okay. I hope you enjoyed that. That's a fun little example of stacks. So now let's talk about queues and decks. Alright, so my goals for you, and excuse me, let's get started with queues. It's a fun little word. It's a British word. So the metaphor is you got a bunch of people, they are British because they use the word queue instead of line, and they're waiting in their shopping line or whatever. Alright, and the way we draw queues is not the same as stacks. We kind of draw a queue like this. This is the common way that I know to draw it. It's like you got some lines on the side that delimit the start and the end, the front and the back. 1, 2, 3. So here's a queue with 1, 2, and 3 in it. And there is a concept of the front, and then there's a concept of the back. Okay? So it's very, very similar. Queues are very, very similar to stacks, but there's one key difference, of course. So here are our queue ADT operations. We got your push, your pop, your front, and your empty. This one's the new one, okay? Not top anymore. It's front, okay? And then the change that we make is pushing. You always push to the back. Okay. Alright, you always push to the back, and then popping removes from the front. Okay, and then empty again is just check if it's empty. Alright, so the way that you implement these things is really not too bad. You will use a list again. It makes sense to use a list. So let me show you how we might come up with 1, 2, 3 from an empty queue. Alright, so here's my empty queue. It's got a front and it's got a back. So if you call empty on it, it'll return true. Looks like a happy face, kind of. So there's our empty queue, and let's push 1. 1 is the first person to this hot dog stand, to this checkout line. They're in the front. Alright, so 1's at the front, front, back, front, back. You might also hear it called rear in some textbooks. So we've pushed one, we push it to the back. Well, there's nobody in line, he's in the front. So lucky one. And let's push 2. We end up with 1, 2, 3. No, sorry, 1, 2. Getting ahead of myself here. So 2 went to the back, right? Front, back. He went to the end of the line. He's a good person. He's not cutting. And then we're going to push 3. And then you know where I'm going with this. We now have a 1, 2, 3 in our queue in that order. And then let's say the person at the checkout who's like ringing everything up takes all of 1's items, and like 1 is now ready to leave. He's paid. He's got his bags. He's ready to go, or he's got his hot dog if this was a hot dog stand. So pop would give us 2, 3. Okay, which is in stark contrast to a stack, because 3 was the last thing we put on the stack. It would have left first. No, queues, everybody waits their turn. Okay, that's pop. And then if we were to go and say, like, if we were to say front right now, where's the front? It's always in the front. It's 2, so it would give us back the 2. Okay, and then of course you can keep on popping if you wanted to, in that direction. Okay, so I guess we should talk about the implementation of push and pop. Front and empty will make sense after we talk about push and pop. And then let's analyze the running time. Okay, so let's see here. How do I want to talk about this? So the idea is, like stacks, a list is a good representation for a queue, because we're able to add things to the beginning or the end of a list, at least a doubly linked list, very fast. Okay? That is the idea, and that is what we want to do. So we want to use lists for this. You can use other things, but it might be slightly slower. So the empty queue we'll represent that with the empty list. Okay, that's not too bad. So deep down, if we had the empty queue, let's go over here. Deep down, if we had the empty queue, really we had an empty list. Okay, that's the correspondence. Okay, and then once we pushed, maybe we push 1. And then it ends up here. We will have a list with just 1 in it. Then we push 2. We'll have a list with 1, then 2. Yeah? So that's that. Let's see here. 1, then 2, and that's all we get. So where do you always push? Which side of the list do you push when we're talking about queues? Well, this one wasn't so obvious, but once the 2 came into play, now we know where to put it. Always at the end of our list, assuming you want to do it this way. I mean, you could do it in reverse if you'd like. So push for queues is push back for lists. Okay, do you see that? That's not too bad. And let's see, pop then. If we want to pop, get rid of the front of this queue. So we're going to pop it. Pop will make the 1 go away, right? So we need to somehow translate this one into just 2. And how do we do that? Well, we remove the front of the list, okay? So pop is pop front. Okay? So now you understand why they're calling them these things. It's the terminology is coming from stacks and queues, actually. But we're using them to talk about lists, even. So that's that. And let's see, what else? Front Well, fronts just go to the list, get the first element. Okay. Or, I guess in your own implementation it would be a dereference of a pointer. It's just retrieving the first element. And then empty lists, some of them keep track of their size. It's just checking if the size is 0, or checking if you have just a null pointer. Okay, so these are not too bad. I hope you understand that we've already talked about the running time for all of this stuff. So push is pushback for lists, constant time. So you just go to the back, make a new node, find the next. Now, even for a singly linked list, it's not still constant. Okay, it's just make a new node, change some pointers around, not a huge deal. Okay, no loops involved. Pop is pop front. That's again also constant for a singly linked list and a doubly linked list. Not an issue, because you just go to the front. Here I am. Well, all right, my new first is going to be what's after it, and I'm going to delete this one node that I'm getting rid of. Not too bad. Front is just retrieving the first element of a list. Deep down, that is, even in the C++ implementation, that's, well, it's constant time, because it's just, you're essentially dereferencing a pointer, that first pointer. If we had it like that first. If you had that, you just dereference it and then get the value at that place. So that's just a couple operations. A star dereference operation, and then a dot, right? Or an arrow if you want to use them both at the same time. So that's a dereference and a dot operation. Okay? So that's, again, constant. And then empty, check if the size is 0. So if you saved inside of your list, like a size member variable, you can either go and check that and update it every time you add something or remove something. Or you can just check that, hey, is my first, like you remember what an empty list is, it's just when first and last are both holding the null pointer. So they're both like pointing off into the ether. There's nothing there, the 0 address. Okay? So all of these operations, and you could understand why if you can make your program look like a stack or look like a queue, you're set because you're doing constant work at every time you call these things, every time you use these member functions, these QADT operations. Okay? Which is beautiful. So yeah, you got constant time there. And queues are kind of the opposite, we've noticed, from stacks. So let's write that. It's for posterity. They are FIFO rather than LIFO. All right? So FIFO means first in, first out. All right? So the first thing that you put in, so in English, hey man, give me the normal quote. Thank you. The first thing you put in is the first thing you get out. Okay? You take out with a pop. Let's say that. Is the first thing you take out with a pop. Alright, so it's like some very nice people that don't cut in line and they're waiting peacefully. Alright, so the first person that was there gets handled first. Okay? That's what a queue is good for. And there's lots of things that a queue can represent. So that's that. They are FIFO, not LIFO. So that's the one main difference between stacks. That's essentially the one difference. FIFO rather than LIFO, understand that, and you'll be able to implement a queue and a stack very easily. You should be able to change your stack implementation quite rapidly, right? You just change some things around, push and pop, and front is not top anymore. You're essentially set already. So that's why I was saying that this is a very, very chill week for us. This is not a whole lot that's new. Okay, so C++, like for stacks, they have implemented the QADT for us. And so here is my British joke, and let us go to the documentation. Okay, let's take a look at what they got. So here we are, and pretty much exactly what you would expect from a queue, normal stuff just like a stack. All right, you got your empty, you got your size, front, back, so it is saving the amount of things inside of it, which may be useful for you, and you can always augment your own implementation with a member variable that keeps track of the size. Okay, so that's that. You can print it out, the dot size, front, back. You can even access the back, but that is not a requirement of the textbook ADT. And then you got your push. In place is a bit fancier. It has to do with like the way that memory is allocated. Not a huge issue for us right now. Then pop and swap again. I'm really not sure about. I haven't tried it before. All right, so let's just have a very quick example of this. I think we're probably all over this now. It's very simple. So your Netflix queue is a queue, believe it or not. So you say, like, I want to watch something, and then right after that, I want to watch this other thing, or your Spotify queue, whatever you're using and can relate to. So, like, maybe you're busy watching show A right now, but you notice somebody like tweets about this cool show B, and you want to watch that too. So you're going to push that to your Netflix queue. And then maybe, I mean, you're like a fiend on Twitter or something, and like you're just trying to get a bunch of people's recommendations, and maybe you push C and D and E as well. And then you're eventually going to get around to them, like after you finish your lab. To watch the next thing in your queue. You'll get it out, retrieve it with front, and you'll, once you're done watching it, you'll pop it. Okay, so that is an example in real life of using queues. All right, you can include queue, be like, push C, then D, then E. No, sorry, B first. How can I salvage this? Let's erase this. B, C, D, E. There's our queue. And then you'll start popping, and the popping always happens from the front, and eventually you'll watch all the shows that you wanted to watch. Okay? So that shouldn't be too bad. You'll just say queue, maybe like string, queue, and then you'll be like queue dot push. I'm bad with letters today, apparently. Push B, etc. Okay, and then eventually it'll be like queue dot front to get that value, and then queue dot pop to get rid of it. Okay, so that's not a huge issue. The one cool example I do want to show you is, let's see here, a queue made up of 2 stacks. And this is like a fun like interview question. This is like a classic interview question, or an example that teachers want you to have in the back of your mind. Classic example. I'd never ask you to come up with something like this on an exam. It's just clever. And if you're a teacher and you're testing cleverness, that's a bit of a problem. So I guess we test problem solving in this class, but not like this example that would require you to be very, very smart to even come up with it. So you've got two stacks, and I don't know, we'll call it S1 and S2. And we're going to model a queue using these stacks. Okay, so we have to talk about what is push, what is pop, what is front. Okay, so push just so happens to be this, and this, I would have never come up with this, that's for sure. So push adds to S1. Okay, you just push to S1, not a problem. All right, pop pops from S2. And I'm going to show you this working in a second. Hopefully I got it right. Otherwise I will stop this video and edit it with the correct solution. If there's something in S2. If there is nothing in S2, pop everything from S1 and push it into S2. That's a key thing. And then you can proceed as normal. Okay? That is push and pop. And let's see. Front is going to be pretty much the same, actually. The same as this. So, gets the top of S2 if S2 has an element. And if there's nothing in S2, pop everything from S1 and push it onto S2. Then proceed as above. All right? That's push, pop, front, and then empty is if both are empty. And I guess I want to try this with you. Why not? Let's give an example first. So let me do a queue, model this queue, where we push 3, then we push 2, then we get the front, then we push 1, then we pop twice. All right, let's see. I think that's what I want to do. That will, no, pop 3 times. Or how about I put a pop in between that front and that push? That's what I'll do. There we go. Do a little surgery there. Now let's watch this work. So it's really weird. So I'm going to push 3. So it's going in S1. I'm going to push 2. It's upside down now because we want the front. Currently our queue looks like this. It's 3, then 2. I'll have some space for our 1 in a second. What in the world? If I pop from this S1, obviously I'm getting the 2, not the 3. It's not the real front. So when I say front, I go and I pop everything from S1 and push it onto S2. So first comes the 2 because that's the one I get off first, then the 3. Okay? And these all come off. Now S1's empty. And I can return the top for my front operation. I can return the top of S2. And it's correct. So that's good. Then pop will remove from S2. So the 3 goes away. Okay? Now I'm here. Push 1 to S1, then pop twice. The first pop is fine. S2's already there, so it did the right thing. It got the 2 off, so now my queue looks like this. Then I just pop the 2. So now this is empty. And then I pop twice. No, sorry, I pop 1 more time, that is. Which means, because S2 is empty, I gotta shuffle everything over, put it there. And you can see why we need 2 stacks now. And then we can finally pop. You can see why we need 2 stacks, because we need to reverse the first stack. Okay? Now, let's see, let me look at what we got left. More or less, not too bad. That should be fast. Maybe we can code this up very quickly. We'll try it all. Maybe I can copy all this. So, gosh, this is gonna be interesting. Yeah, undo. Okay, so there's my comments. How do I want to do this? Include stack. And let's just be lazy and implement this in just a class that's simple. Call it weird queue. So the one thing that it has inside of it is two stacks. S1, S2. That's that. And honestly, let's make it templated right now. Why not? Work for anything. Then we'll do constructor is not necessary because we're already default constructing these properly. Push. We'll take the T and push it. Then void pop. Then T. Sorry, front. And maybe we can make it a T reference so that we can potentially change it if we wanted to. Then empty. Empty's easy. It's just return s1.empty and s2.empty. They're both empty. This will be true, and the whole thing's empty. All right, push. Well, let's do you. Let's make you work. Push. We need to just push to s1. So s1.push t. All right, then pop is going to, if s2.empty is not true, then we will just pop from s2. Otherwise, we got to bring everything over from s1. So we're going to say, while s1 is not empty, push it on s2, and then pop. All right, so that'll reverse everything over on s2 now. Oops. This one is reversed on s2, and then we can do what we did before. We can just say s2.pop. And this is all essentially going to happen again in the front operation. Okay? But instead of popping, we're going to return the top. So I'll just copy and paste all this. Whee! Super rapid code, but I'm implementing all of this. Hopefully it's going to make sense. S2 dot top, return that. This all needs to happen the same. You got to move everything over if it was empty. Then again, return s2 dot top. All right, then we get the thing on the top. We're set, and now we can have a main function. So let's see here. Weird queue events queue. Queue dot push. What was my example? 3, 2, 1. Push 3, push 2. Then I'll see out doing the front. Make sure it was 3. Then we'll do pop. And I'll just remember to keep on printing out the front, just so that we get to remember it by that. Okay? Pop those times, pop, 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 and one more pop. Okay, now it's empty. And let's see if I did anything horribly wrong. Oh, yes, I sure did. Let's see what I did. Dun dun dun. Well, S1's not empty. Well, S1's not empty. We're going to push the top. And then pop from S1. Let's see. Oh, maybe I popped too many times. Oh yeah, I never pushed the 1. Sorry. That is kind of necessary. Push 1. Where do I do it? After the front? Yeah. And the pop? Front, pop, push 1. Then I have a 1 at the end and then a 2. So I can have at most 3 pops. Yeah. Okay, that seems right in my mind. And this last one is 1 for true. It was empty. Okay, so that's where I want to leave you today. Hopefully that was exciting. I would have never come up with this. Some very smart people did, and I will not test you on it. So that's where I'm going to leave you for this lecture, and I will see you in the next one.